I have already written the plan of the lecture, so I will first not hurry and try to come back to some of the elements of lecture 0 and 1, because I had rumors that some of the notation were a bit difficult to grasp, so I might review and give more examples. And then, before starting the subject of the proper subject of the lesson, I will give you just a hint, a little idea of a notion of general connective that helps also to understand the general structure of this syntax. Okay? And once this is done, we will embark on classical logic. So we will essentially get a system for classical logic by removing the restriction on contraction and weakening that is present in linear logic. But then we are faced with the funny classical logic, which has two conjunctions and two disjunctions. So some people may think that it is too much, and we can indeed reason with a subset of rules, because after all, one conjunction is enough and one disjunction is enough. And I will show you how good it is to take all reversible rules and forget about the irreversible ones. I will show you, well, I will not do anything with the other choice, but just mention that Gensen, in his papers, has this choice. And finally, keeping both is a good key to having this computational consistency problem solved. So that's where we will stick to such a system that has two conjunctions and two disjunctions, and then we will discuss how to make it a confluent system so that you don't identify too many proofs. And this will rely on the notion of focalization that you have seen this morning. And then we will discuss a variation of this system which I will call indirect. So we will see when we come to it. And once we have this system, I will discuss encodings from and to this system. So first to this system. So as I told you, I consider this syntax as an intermediate language. So it means that it should be the target of translations from ordinary functional programming. So we should be able to translate call by name and call by value lambda calculi. And I promised to explain some links between this syntax and the operational semantics of the lambda calculus expressed in terms of abstract machines. So I'll do a little bit of that. And finally, I will show how to translate this syntax into intuitionistic logic, which is usually the last step. Well, if I put together the translation from lambda calculus to system L, and then from system L to intuitionistic logic, together this forms a translation from logic, classical or not, into intuitionistic logic, and this is what is usually called a continuation passing style translation. And we will see that the last step, this step, is almost trivial, almost textual. So in some sense, this language, system L, is already a CPS target language. That's more or less the idea. Okay, so let's start with a review of lecture 1 and 0, and 0 and 1. And when this is done, I will leave space for questions, okay, before I go on. So let me remind you my short introduction to linear logic, where I insisted on, I followed the historical, even if the history is short, it was born in '86, so it's like 25 years. The historical line is to divide connectives in multiplicatives, additives, and and exponentials, and I explain the terminology. And I improve the slide by giving you a table, because our discussion in this series of lecture is more along the distinction between irreversible and reversible. And I want to show you through this table that this goes completely orthogonally to the distinction between multiplicatives and additives. That means that the two multiplicatives, one of them is irreversible, the other is reversible, and the same for additives. Okay? So again, the distinction that will matter for us is between irreversible and reversible, and we will really exploit it when we come to this line in the lecture, when we discuss focalization. That was the first thing. Then I wanted to give you an illustration of the syntax, because I talked about active formulas and some of you were not very clear about what it meant. So let me just, it's not a meaningful proof. I'm just thinking of a proof that ends like this. Okay? So it's a proof of the sequence n plus p tensor m, a par b, gamma 1, gamma 2. And suppose that this proof, the last rule used was the tensor rule. So you introduce a tensor last, and then after this, in terms of proof search, you decide to decompose the power. Okay. So let us see how the syntax of system L is going to transcribe this. So in order to account for the first rule, I will suppose that I have a proof of the assumption n plus p a b gamma 1, and this will be a given command C. And now I will use the rule to introduce the power, which is a reversible connective. So remember, for reversible connectives, I use binding constructs. So then I get this mu y1 y2 dot C, which is a term of a par b in the context of the other formulas, n plus p and gamma 1. Okay. And y1 and y2 were the names associated with the assumptions A and B. So now you see that if I want to progress in my transcription of the proof, I must change the active formula, because the formula that is going to be active in the next rule is not A par B, but N plus P on the left. And on the right is going to be M. So I need to play this little game of deactivating A par B and activating N plus P. So that's why my picture here is much more verbose than the one up there. Instead of having 3 lines, I have 5 lines. So let's first do the deactivation. So the trick for deactivation is just to cut this term with a variable. So instead, now you can think of this variable as a placeholder for the formula A par B, and the result is a command where y is cut against mu y1 y2 dot C, and this becomes again a neutral thing where nothing is activated. And now I need to activate N plus P, so I use the mu, which is the activation construct. So mu, and I use mu x, because x is the name of N plus P. So mu x of all this command is going to be of type N plus P. And now I can assemble this term with the proof of M gamma 2 that I'm supposed to have around. So by pairing them, I get a proof of the sequence. So I hope that you can better understand how the syntax works through an example like this. Okay. So the second remark I wanted to do is that I listed these reduction rules, and I only insisted on the pattern matching aspect of the rules, which is an interesting feature. But some people asked questions about what is the role of substitution here, and I have prepared a slide to answer this a bit more precisely. Okay. So what I want to do is to explain you the first two rules. So let's do it slowly. So there is a lemma which is not so completely trivial to prove. It's not difficult, but you have to do it with care. So exercise. It's on induction on the proofs. You can show that for any command that has a type x colon A gamma, then I know that x occurs uniquely in C because the syntax has been designed to be linear. So it's also an easy exercise to check that an invariant of the typing rules is that in any term C of a given type, if a variable occurs in the context, then it must occur in C, and it must occur exactly once in C. Okay. So now the lemma says that C, this occurrence of x in gamma is always of the form x cut with some term t as a subterm. Okay, so C is a big term that contains a subterm of the form x cut with t. And this x cut with t corresponds exactly to the transcription, the syntactic transcription of the moment where this A was active, where this A was actually introduced. Okay, that's the idea. So now that we have this lemma, we can read this computation rule, which says that T1 cuts against mu x dot C returns C where T1 replaces x. What does this mean? More concretely, well, if I replace C by this context, okay, and if I do the substitution now of T1 plus in this context, the result of this reduction is actually to have plugged T1 plus exactly in contact with T2 minus. So you have to think, maybe I should draw a picture. You have to think that, so this was T1 plus, and this was mu x plus dot C, and somewhere in the proof of mu x dot C, at a certain moment, there was x T2 minus. So here's your cut, which you want to eliminate. So in sequent calculus, this case is known as the as the commutative cut rules. So while the third or the fourth rule express what is called logical cut elimination, where you actually see something happening right at the cut, because you have been introducing on both sides the formula that you are cutting, so then you can do immediately something, while in the first or second case, we are accounting for the fact that this cut is not quite ready to know what to do. because this formula may have just been introduced right now, we can believe it, but the presence of this mu x plus says that this was done earlier for, not exactly there for the other cut formula. So by substituting, what I actually do is to let this cut go up towards meeting the appropriate moment where the cut formula was introduced. So the cut moves towards the moment where the formula was introduced on the dual side so that some real interaction can occur. So in other words, in these rules, you have to consider the third and the fourth rule as the real ones that do computation, and the first two as some control rules that acheminer, how do you say this in English? That put you on the way to actual interesting cut elimination steps. Okay? And they are called control rules because you see that if you apply the first rule, then you are going to let the cut go up on the right, while if you apply the second rule, you are going to let the cut go up on the left. So you decide on where the control of your cut elimination is going with these rules. Okay, so I hope also that this is helpful. And so there is a slogan here, which is that in this syntax, the substitution operation accounts for all the commutative cuts, the management of commutative cuts that you find in sequent calculus books or papers. Okay. So then I must recall you that I also tried to discuss the question of confluence, and I showed you I tried to analyze one of the critical pairs that arise in linear logic, and there are actually two other critical pairs which I didn't highlight, but they are on the first line, and you can believe me, they can be treated well. But there's one critical pair which, if it would be there, would really be harmful. So the critical pair that is avoided by linear logic is the critical pair where you have weakenings on two sides, or actually weakening and contraction on any of weakening and contraction on two sides is bad. So let me just illustrate this and just make sure that everybody sees why linear logic forbids that. So the really bad critical pair, which we don't have in linear logic, but which we will face when we remove the restriction on contraction and weakening, is this one. So it's a really stupid kind of cut. So suppose that A has been introduced by weakening on the left, and that A has been, A bar, has been introduced by weakening on the right. Well, both on the right, but on the left assumption and the right assumption of the cut rule. Okay. Then, essentially, the only sensible rule for weakening is the one which is written here. The number, the last before the 1, 2, 3, 4, 5, 6 rule. So it's easy to see that if I just put anything here, the best way to eliminate this cut, I don't know exactly how this was built, The sensible way to eliminate this cut is to say, well, I started from this assumption and also this one. But I have a very simple way to reach the conclusion gamma delta, which is just to apply repeated weakening from gamma. So that's how you eliminate this cut. You essentially forget this proof. Okay? So, but if, now remember that control can go on two sides, and here we also have the same problem. Suppose that on both sides this has been a weakening. Then I could also decide, so essentially what is written here is that the result of eliminating this cut is this proof here with some weakening. But I could equally well have said that the result, because I could now decide that this is the guy who takes control, and this could also reduce. So it reduces on one hand to this one, and it reduces also to the proof so we have two proofs of the same conclusion gamma delta, which are obtained from this unique proof, and you will admit that they are widely different, because this was any proof of gamma, this was any proof of delta, so essentially you end up by identifying any proof with any proof of any formula. So this is really, really extremely bad. So we should do something about this. Why does linear logic do something about this? Well, just because weakening is only allowed on a why-not formula. And the dual of a why-not formula is not a why-not formula. It's a Bang A bar formula. But you are not allowed to do weakening on a Bang A bar formula. So this is a more precise explanation of the claim I gave yesterday, that linear logic solves this problem of conference through typing, if you want, through more information on the formulas. Okay, and we will solve it in a different way for classical logic. Okay, and since we'll solve it in a different way, I'm not anymore concerned even about making these critical pairs converge. Because what we are going to do is to present you a system that has no critical pair. So the system will be, the operational semantics will be restricted in the way that there will be no critical pairs. So since my insistence on linearity of the syntax was linked to the fact to solve these critical pairs, because it was important then to use linearity to keep track of a kind of lozenge of reductions, I'm not committed anymore to linear syntax. So what I shall do is, I need to get this out now. No, not yet. Not yet, because I need something else. Okay, so I'll do this here. I'm going to rewrite the syntax for contraction and weakening, and to make it simpler. So remember that I had an explicit syntax for contraction and weakening. So now I will just use, and I do this for classical logic right away. So for the weakening rule, I will just say that if C is a command of type gamma, then I can weaken by just writing mu alpha dot C of type A gamma, where alpha is a dummy fresh variable. So that's my first violation of the linear syntax. Now I allow variables not to appear. Okay, so alpha does not appear in C. And for contraction, I'm violating the second dogma of linearity, namely that if I have C of type gamma, x1 of type A1, x2 of type A2 gamma, then, it's AA, then mu, yes, that's mu x dot C, where x replaces x1, x replaces x2 of type A gamma. So I now use also the mu construct, and I'm violating the fact that x occurs only once, because now x occurs at least twice, okay, in this term. So in other words, I can use the kit of the mu construct to deal with weakening and contraction implicitly. So that's less bureaucracy in the syntax. Okay, so once this is done, I have a last thing to show before removing the screen, because the rest of the lecture I'll try to do it on the board, and in the end I'll need the slides again. Okay, so I promised to give a very short view of general connectives. So there is somewhere here where this is, just to know where it is. Not sure where it is. Maybe it would take less time to just do it on the board. Yeah, I won't find it. Okay, so let's remove and do it on the board. So I don't know how to do this. Stop. This red thing. Yes. Okay, so just a rough idea of what a general connective could be. Okay, so I can remove this because it's written here. So it's not quite as general as it should be, but it's enough to give an idea. So I will define a general connective. Well, I will define an arity, a notion of arity, for a general connective. And this is not the last word on it, it's just a first approximation of this idea. But in the time frame that I have, I will not develop this further, but there are more indications in the set of slides. So an arity for a general connective is a sequence. A number is a sequence of numbers. Of course, a finite sequence of numbers. Okay, so we could write it like a family Ni where I belongs to I. And what does this indicate to me? Well, it indicates to me that for each I in I, there will be a constructor. So, for each I in I, there exists a constructor. And this constructor will have arity Ni. So, it will take Ni arguments of Ni arguments. Okay? And whatever big I is, there will always be only one destructor. So there exists exactly one destructor. And this destructor is going to be ready to do a case analysis on all the constructors. Okay, so it's just like in an inductive type. So let's, rather than, and I can give you, so the destructor has this shape. So let's call me this constructor Ci. Okay, so the syntax of positive terms will be, because remember I use constructors for irreversible connectives that is the same as positive. Okay, so the syntax of positive terms is going to be enriched with these constructors. So you have a constructor Ci that takes a T1 and then Tni, and then so that's one of the additional cases that you have in T plus. And in the negative terms, you will have this unique mu, which has this form Ci of x1 xni dot Ci, etc. So for each, sorry, okay, so sorry, it's not very good to have both C for constructor and C for commands. So let me use chi for these constructors. Okay, so there is a constructor, I will use the letter chi. So the mu constructor has this form. It's a list of binding constructs of the form ki of x1 xni dot ci. And then the computation rule is that if you match the constructor ki of t1 tn against, so these are actually pluses, against this mu, this big mu thing, so what the rule does, it does two things at the price of one. It does record selection, field selection in a record. So it says, oh, we are interested in the I component. This could be seen as a record, which has at field I has this information. So I'm going to select, because I'm against this I constructor, I'm going to select this part of the term. And second, I'm doing the pattern matching. So then this results in T1. Okay. So now if you remember the computation rules that were given for the tensor and for the plus, you will see that they fall in this general scheme. So let me repeat them here. So for the tensor, it was T1, T2, mu x1, x2 dot C reduces to C, where T1 replaces x1, T2 replaces x2. Then for the plus, it was in left of T1, mu in left of x dot x1 dot C1 in right of x2 dot C2 reduced to C1 where T1 replaces X1. And similarly for in right of T2 blah blah, which reduces to C2 where T2 replaces X2. It's a very easy exercise to check, well, maybe someone can tell me, what is the arity of the tensor according to this definition? Huh? Singleton 2. And what is the arity of the sum? It's a sequence, the sequence of 1, 1. Yes. Okay, so it's just to give you a rough flavor. The real picture, which is actually the one which I like, is where I have more information. Instead of having numbers, I have actually sequence of signs, and these signs are of 4 kinds. They give me an indication of being left or right in a sequence, and they give me an indication on being positive or negative. So I have 4 signs. Positive on the left, positive on the right, negative on the left, negative on the right. So instead of having a number ni, which is like just a sequence like this, for each of these dots, so here it would just be the number 6, I have actually a sequence of 6 signs. Okay? And moreover, also I have a sign which tells me in which syntactic category the constructor is going. Okay, but I'm not going to do this in detail. Okay, so now I'm ready to discuss the question of classical logic. Yes? Oh, yes. Oh, sorry. I also said that you could ask.
A question on the previous model. Why is it so important to ensure contours?
Why? Sorry?
Is it so important to have contours?
Well, if you want, what we want is to have a system where we don't identify everything. So we want to, the minimum that we want to give a denotation of semantics to any system is that, for example, if you have this, so you have 2 proofs of A by projection. You don't want them to be the same. Okay? If the 2 projections are the same, it's really, you have nothing. So that's the idea. You don't want to identify everything. And confluence is something that guarantees. Yes. Okay. By confluence, you know, if you know that 2 normal forms will not be identified. So you have some basis for working on. Okay. So is there any more questions on the basics of the syntax? Okay, yeah?
I don't really see that I don't really see the relation between fidelity of the system and confluence.
Well, if the system is confluent and normalizing, which we will see, then normal forms are all provably unequal. They are not provably equal.
Contour example, no confluence and fails to become trivial, just to get an idea of the time frame.
No, for me, confluence is really that's part of the agenda of a decent free theory work. My difficulties in following. There was a hope that maintaining non-deterministic systems of classical logic was still something interesting to study, but I haven't seen any interesting sign that it was really interesting. Okay, so I have written down the system as we had it for linear logic, except that I have removed the exponentials and that I have now the unlimited weakening and unlimited contraction with this non-syntax for them. I mean, I don't have special construct for them. I just use a mu. Okay, so let me first discuss what would happen if I decided. So it is, as I said in the first lecture, it is an easy exercise to show that in the presence of these two rules, you can interderive this conjunction rule and this conjunction rule. These two are interderivable. So you might want to decide to go only for the reversible ones. So let me try, for example, to just take the reversible ones. That's the reversible conjunction. That's a reversible disjunction. And I'm going also to do something else. I don't take the cut. And I'm not taking term decorations here. So maybe I should just extract this right here. So I'm just extracting this form of disjunction. And I will call it OR, because I just take one. And I'm extracting this form of disjunction. Yeah? Sorry? So which color is possible? The blue doesn't seem to be available. Or another red. But this red doesn't work. Yeah, thank you. And let me extract the axiom, but with the weakening. Then, quite interestingly, this system is complete for probability. And the proof is trivial. Or it requires a few lemmas, but it's trivial. It's an exercise. So I give you a hint for the proof of the exercise. Yeah, I don't even need the contraction. It's going to be admissible for this system. So the reason is the following. You attempt, so of course it's going to be sound, because all these rules are written to be sound. So now the question is, if a sequence is valid, if I know that this sequence is valid, then there is a proof attempt which will succeed. Now, what happens here is that because the rules are reversible, you are going to develop your proof attempt in any possible manner. This doesn't matter. They are all to be as good as the others, because everything is reversible. And while you develop your proof tree, you keep an invariant. You maintain an invariant, which is that all the leaves of your attempted proof together are valid, because they are equivalent to your first sequence, which was valid. So because the rules allow you to decompose formulas up to the atoms, you actually end up with sequence that only have, when you fully develop your proof tree, you have sequence that only contain atoms. And then it's a very easy lemma to show that a sequence that contains atoms is valid if and only if it has the form of an axiom. So a sequence that contains only atomic formulas is valid if and only if it contains two atoms, one of the form X and the other of the form X bar. And that's the end of the proof. So they are good at something. The all reversible presentation is nice, but doesn't lead to any good computational properties. It's about completeness of probability, which is a good thing, but doesn't lead to anything. Now, as I told you, I think, because I'm not sure, I never read really the old papers, but I'm pretty sure that Genson's presentations were based on having only the irreversible presentations of the connectives. And one of the reasons why he wanted to do this, oh no, I don't know. It's just like this. Okay, and then I think that we need to keep both. So now we will start to work on focalized classical logic. So what I shall do in the next 10 minutes is to restrict the space of proofs and to restrict the computation rules. I could actually dispense with restricting the space of proofs and just restrict the operation semantics. So the second aspect is more important. But somehow I'm used to do both, and it goes well with the spirit of the lecture of this morning as well, because this morning probably, even if I was not there, but I have read the notes of Frank and heard his lecture last year, one of the concerns that he has is to let the space of sequent calculus proofs match the space of natural deduction proofs. And since there tend to be many more sequent calculus proofs, focalization is a way to trim this to get a kind of one-to-one correspondence with natural deduction proofs. So that's good motivation. And I want to follow this spirit, and I want also to trim the possible proofs here. So what I'm going to do is to be very syntactic, because I also don't have too much time. So I will do this very, very syntactically. So instead of having three categories of terms, which were C, T plus, and T minus, that's what we had before. Then we are going actually to do something else. We are going to do C, V plus, T plus, and T minus. Okay? And I will need an auxiliary definition, which is that V is the same as V plus or T minus. Okay, so I will use V to stand either for V plus or T minus. So these will be called the commands. These will be called the positive terms. These will be called the negative terms. And these will be called the values. Okay. So commands, there is no change. A command is only of this form, T plus, T minus, which I don't mind to write also in the other way around. It's not a problem to write it this way or the other. Okay, so now the line for T minus is not going to change a lot. So I should probably have, well, anyway, I write it directly. So the line for T minus is the same as you have seen in the slides. So a T minus is either an X minus or a mu X plus dot C, or Okay, so these are the terms corresponding to introducing the negative disjunction, the negative conjunction, no, negative disjunction, and here the negative conjunction. And here we make a dramatic change. So a term is either going to be a mu or a value. So a value is a non-mu term. And now a value is going to be defined by some hereditary way. So you probably have got from a lecture of this morning the idea that in a focalized proof, when you are decomposing a positive formula, you are committed to do this in a consecutive way until you reach a negative subformula. So you have this notion of focus where you cannot change your mind and try to decompose another formula while you are decomposing a positive formula. So I'm going to give an exact syntactic account of this. So a value is either a variable, and so previously I just had the pairing of two terms T1, T2. That was a term of type tensor. So this is not possible anymore. Now it's going to be a V1, V2, where V1 and V2 are in this category. So that means that if V1 is a negative term, it's okay. But if V1 is a positive term, then it's a real constraint. If V1 is a negative term, then, well, it's just as in the previous syntax. But if V1 is a positive term, then it must be a V plus, which means that it should continue to be of this form. So that's exactly what the notion of value should be. What is a value of type A times B? It's a pair of two values, one of type A1 and the other of type A2. But if A1 is itself a product, then this value must be a pair of values, etc. So this is the reason why we call them values. And the same for in left of V1. So typically, let me tell you what I forbid. I forbid to form the term in left of mu x minus dot c. This is illegal in this syntax. So I'm restricting the syntax. And I think it's all. That's the syntax. So this is restricted syntax for focalized proofs. So that's the syntax. Now I will design the proof rules accordingly. So there will be a fourth judgment. So far we have seen, we had three categories and three judgments. Now we have four judgments. So maybe I should have, written them here. So corresponding to these four categories, here we will have the judgment that C is a command of type gamma, that V plus is a value of type P, and it's going to be written like this, with instead of the bar, there will be a semicolon, no, not semicolon, how you call it, a semicolon. Yes. And this has a name in the literature, it's called the stoop. It's a special place, just like a stoop is a special place in a church. It's a special place in a proof where you should behave in a certain way. And so that's a new judgment. And then the old judgment still exists, a positive term, and the old judgment still exists, a negative term.
Could you write a bit louder?
Yeah, okay, I'll try. So I hope that this is large enough, because I'm going to overwrite it. So I'm going to modify the proof system accordingly. The formulas are the same, but now I will use another abbreviation. So remember that I use the abbreviation that V is either a V plus or a T minus. So accordingly, I will use this judgment V double bar gamma. It's just for the sake of a few minutes. This funny judgment will disappear when I go to indirect time. This stands for two things. If V is a V plus, then it stands for V plus gamma with the semicolon in the stoop. Or if it is a T minus, it stands just for T minus is a term, a negative term. So it's just to put these two cases together. So now the rules look as follows. In order to form the tensor, I need actually to have a V1 and a V2, not an arbitrary T1 and a T2. And this V1 must be typed according to the discipline. Okay, and here this is in the stoop. There is no change here, no change here. Here the same thing. This should be a V1, and this should be in the stoop. And there's one rule missing, which tells me that any value is a term. So there's one additional rule, which I'm going to put here, that if I have that V is of type P gamma, then I also have that V of type P is a term of type gamma. So it's similar in spirit to the rule that we have seen in linear logic. We forget the information that we are in the stoop somehow. We forget something. Okay. So now this is so far for reducing the space of proofs. Now I will reduce I also will reduce the operational semantics. So for the operational semantics, probably I'll need to use the beginning of tomorrow morning to finish the program today. But I prefer to go more slowly because yesterday I was told to go too fast. So anyway, so the first rule is the most important. It's new, because this category did not exist, V+. The second rule is as before. Is it sensible to write? Yeah. And I'm stopping here because I would like you to notice that with this system, I'm not going to have any critical pair anymore. Because you remember one of the critical pairs that we have analyzed for linear logic was this one. Okay? And this critical pair is extremely dangerous when x does not occur in C and C1, C2, and y plus does not occur in C2. Because that's then the weakening pair which I already warned you against. So this pair is extremely dangerous, but it's not there anymore because I'm not allowed to reduce this one when it is this term, which is precisely a non-value. It's a T plus, which is not a V plus. So, because I have this special regime that says that positive variables can only be substituted with values, while negative variables can be substituted by any negative terms, I'm getting out of the non-conference problem. I'm setting some discipline on the way that cuts should be transported during the proofs, and I'm forbidding some of the reductions. Good. And then the rest is as before. So that was the key. The other rules are as before, just respecting the call by value regime for x plus and call by name regime for x minus. So now for a pair, I know that it is V1, V2. Yes. Mu x1, x2, C reduces to C where V1 replaces x1 and V2 replaces x2. And here, this is really one of these two cases because a V is either V plus, in case it will be V1 plus replaces x1 plus, or it is a T minus, in which case it will be a T minus which replaces an x minus. So it's one of these two cases. And similarly for in left of V1, I don't repeat everything, we have seen this already. Okay, so that's the operational semantics. And we don't need anything else. No. So we are here. We've got a working system for classical logic that only manipulates focus proofs and that computes with them. And we will show tomorrow that cut can be eliminated so that we really have a strongly normalizing system. And it is confluent by construction because there is not a single critical pair in this system. Okay, so what is new in this work? Well, it's a work that is going on since 2 or 3 years. What is new is the syntax. The underlying logic is essentially the one of Girard, which is called LC. So the main effort that I'm describing and emphasizing here is a syntactic decoration and understanding of this work. Okay, so let me move. I think I still have about 10 minutes, even a bit more because I was eaten 5 minutes by the vote. But I would like also to leave some space for questions. I think I want to go as far as here, for sure, and to give just a pre-announcement of the encoding of CBN and CBV. And we will do the last 3 points as a first half of the next lecture. Okay, so what I want to do is to make a further little change, which I can explain here. I want to avoid this funny thing here, and actually to have this, which sounds a little bit more easy to grasp. A pair of values is a value of type tensor is a pair of values. And I want to have this as well. So I want to forget about this. I want to do this in a simpler way. But then actually this will be a P1 because the value is always of positive type. This will be a P2. This will be a P1 tensor P2. This will be a P1. This will be a P1 tensor P2 plus P2. So that means that actually my syntax of formulas is going to be also seemingly more restricted. And similarly here, these are going to be negatives. These are going to be negatives. So in other words, I want to move from a world where I can tell the sign of a formula just by its head connective. I want to move from this to a world where the connective itself has a polarity. I want to say that the tensor is a connective that takes two positives and gives me a positive. This is, from the semantic point of view, it seems to be more reasonable. But at the same time, I would be very happy to be still able to account for a thing like this. I still want to maintain the possibility to do the tensor of a negative and a positive. But I want to do this with explicit signs. So actually, in order to account for this, I will not do this. I will write explicitly down n tensor P. So I will introduce two modalities, not to be confused with the modalities of linear logic, because they don't play the same role, which are downshift and upshift. Okay. And I need to give you now the rules for these two connectives. You may be surprised to see that a negative assumption is named by positive variables. But think of the axiom. The axiom tells me that from the, it's written here. So I have, for example, that x plus is of type P under the assumption that x plus is of type P bar. That's the reason why x plus in a context it has a negative type, in order to make x plus as a term to make it a positive term. Okay, so I think I'm ready to, now I have almost, I think everything is okay. Yes. So I need now to give the rules for this. But in order to give the rules for this, the best is to see what happens. So we could do it here. What happens in a focus proof? So suppose that I have to decompose n tensor P, gamma delta. And I'm in the soup. So that means I'm really working on this positive formula. And what I would write in terms of proof search would be something like that. Because P is positive, I maintain the focalization constraint in the further proof attempt. But here, because n is negative, I'm freed from the constraint. But it's with this decomposition, it is more sensible to do an intermediate step, which is to write this down n here, and then to say that I'm arriving to this formula, which is still in the stoop, and then, because this is going to be the rule for the down connective, then I have this. So that's the rule. So I'm going to plug it in here. So if I have I'll write the term after. Need maybe to so if T minus is a term of type n, then T minus down is of type down n gamma. And that means in the syntax, I'm going to add one case to the V plus. Okay, I'll do it just right after. And the other rule for introducing the up one is going to be if C is of type x minus dot p gamma, then mu x minus dot c so you see again the same choices in the syntax. This is positive, irreversibles, hence I use a constructor. This is negative, hence I use a binding constructor. And then in the operational semantics, I have one rule which is again in the same kind of scheme that we have seen for general connectives, except that my very first attempt of general connective is not powerful enough to take account of such a connective that changes the sign of the formula, but the more advanced notion of general connective will do. So we have that T minus down mu x minus down dot c reduces to c, where T minus replaces x minus. Again, it's a pattern matching construct, and I destroy the this downshift decoration in the process of applying the rule. Okay, so once this is done, I now have a system, so now it's complete here, which we call system in indirect style. And one of the reasons for calling it like this is that you will see that encoding the system in indirect style into intuitionistic logic is going just to be a kind of jeu d'écriture in French, so that means just to play with words, but essentially to do some kind of textual transformation. Okay, so what I want to do is to just add these two cases, and this one here. And what I just want to do now is to give you a short preview of call by name and call by value implication. So if I want to explain A implies B to my logic students who are not especially trained in type theory or constructivism or whatever, I will tell them that this is not A or B. Okay? And the question is, I can do this in a positive way, and I can do this in a negative way. So if I do this, so this OR is going to be a power. Okay? So I will try to write P bar par Q. And I will try to write M bar par N. But this, in my indirect style, I cannot do this. I must be more explicit, because par is a negative connective, so it cannot accept M bar, which is a positive formula. So this should be like this. So this is the official definition of CBN implication in system L. And for the implication, for the call by value implication, I'm allowed to use P bar, which is negative, but I'm not allowed to use Q. So I should make it, sorry, something is, no, that's correct. No. Okay, so is it correct? This is negative. This is incorrect. I turn Q, which is positive, into negative with the upper arrow. This is correct. So you see that I used two different encodings for two different notions of implications. And what we shall do tomorrow is I will exhibit you terms for the lambda abstraction for the application that are actually macros corresponding to this complex decomposition of the implication. Okay, so I'm stopping here. Questions? Yeah?
Is there a need for shifts? It looks like a bit of a tank.
Yes. So yes, there's definitely this idea that you consider a term as a value. Okay. So it's precisely this guy, which was just a term, considered now it as a value. You freeze somehow it as a value. There's definitely this kind of explanation. And there is also a connection between, so these two connectives together form a kind of adjunction at a syntactic level. But if we were doing the semantics of it, it would be real adjunction. That means together they form a monad. From adjunction you get a monad. And this monad, in the setting that I'm presenting here, is just not an arbitrary monad, it's a continuation monad. It's another way to say that this indirect style is leading me to the usual kind of double negation translation. Okay, but I'm still not doing it completely explicitly. I'm doing it without the language of monad. So that's one thing. And the other interesting thing is that if my language was not so expressive as it is here, if, for example, here it's very expressive it's expressive enough so that I have as many negative formulas as I have positive formulas. So that means my syntax is self-dual. But suppose that it were not self-dual. This is, for example, the case of old lady called by push value, which does not have It has different categories like this, and they are not due to each other. Then, it appears as a sublanguage of this. You have information on this at the very end of the slide that I will send today, later today. You should get them if someone is on.
They're on the website already.
Oh, they are on the website, but maybe not the latest version. Not the one, because there is one from last year which contains much less. Anyway, in the case of Levy, push value, this monad is not constrained anymore to be the continuation monad. That's why he can account for many effects. Because then, this is a monad, not necessarily the continuation monad. So that's interesting to have different views of what the shift does according in which logical system it is. And he calls them in a different way. He calls them the two functors. He has an adjunction with two functors U and F, but they are the same. Other questions?